Continuing on physical chemistry, chapter 4, we're beginning section 5 now. We're going to be talking about thermodynamic relations for a system in equilibrium. So first, the most basic equation, the differential of internal energy is just the differential of heat plus the differential of work. That's the first law of thermodynamics. Now remember, dq reversible is equal to temperature times the differential of entropy. Now here's some other equations that are important that we're going to use in this chapter. So the differential of internal energy is temperature times the differential of entropy minus pressure times the differential of volume. Enthalpy we defined as the internal energy plus pressure volume. Helmholtz free energy is defined as internal energy minus temperature times entropy. Gibbs free energy was defined as enthalpy minus temperature times entropy. The heat capacity at constant volume is equal to the partial derivative of internal energy with respect to temperature holding volume constant. And the heat capacity at constant pressure was defined as is equal to the partial derivative of enthalpy with respect to temperature holding pressure constant. Now if we have any process such as pressure or volume or whatever held constant, then the heat capacity for that process is just equal to the differential of the heat of that process divided by the differential of temperature. Or we could say the differential of the heat with respect to temperature. Now the change in entropy, the finite change, delta means finite change of entropy, is equal to the reversible Q divided by temperature. So dqx is equal to TdS of x, where x is any process. So the heat capacity of x is equal to temperature times the differential of entropy of that process x divided by the differential of temperature. So we get temperature times the partial derivative of entropy with respect to temperature holding whatever constant, pressure, volume. So we get the heat capacity constant volume is equal to temperature times the partial derivative of entropy with respect to temperature holding volume constant. And the heat capacity at constant pressure is equal to temperature times the partial derivative of entropy with respect to temperature holding pressure constant. Now let's talk about the Gibbs equations. Now these are for equilibrium process or reversible process. So we already said that the differential of internal energy is equal to temperature times the differential of entropy minus pressure times the differential of volume. We're going to call that equation 1 to refer to it later on. Put a box around it, it's kind of important. Okay, so we have enthalpy is defined as internal energy plus pressure volume. Helmholtz was defined as internal energy minus temperature times entropy. Gibbs free energy was defined as enthalpy minus temperature times entropy, which is equal to internal energy plus pressure volume minus temperature times entropy. We want to write down the differential form of each one of those. So we have the differential of enthalpy is equal to the differential of internal energy plus pressure times the differential of volume plus volume times the differential of pressure. We're going to substitute in using equation 1, so that gives us temperature times the differential of entropy minus pressure times the differential of volume plus pressure times the differential of volume plus volume times the differential of pressure. Notice these two cancel out. So we're left with the differential of enthalpy is just equal to temperature times the differential of entropy plus volume times the differential of pressure. We're going to call this equation 1 to refer back to it in a bit. Likewise, doing the same thing with Helmholtz free energy, we have the differential of Helmholtz free energy is equal to the differential of energy minus temperature times the differential of entropy minus entropy times the differential of temperature. Substituting in using equation 1, that gives us temperature times the differential of entropy minus pressure times the differential of volume plus temperature times the differential of entropy minus entropy times the differential of temperature. Notice these two cancel out. So we end up with the differential of Helmholtz free energy is equal to minus pressure times the differential of volume minus entropy times the differential of temperature. We'll call that equation 3 so we can refer back to it in a bit. Likewise, the differential of Gibbs free energy is equal to the differential of enthalpy minus temperature times the differential of entropy minus entropy times the differential of temperature. And that's equal to the differential of internal energy plus pressure times the differential of volume plus volume times the differential of pressure minus entropy times the differential of temperature minus temperature times the differential of entropy. We just put back in using equation 1. So after cancellation, we're ended up with the differential of Gibbs free energy is equal to volume times the differential of pressure minus entropy times the differential of temperature. We call that equation 4. Now to remember all these equations, we have a mnemonic called the thermodynamic square. So remember, when we first learned internal energy, we were describing it as a function of temperature and pressure. But now using these equations, we're considering internal energy to be a function of entropy and volume. So we have internal energy as a function of entropy and volume. We have enthalpy as a function of entropy and pressure. We have Helmholtz free energy as a function of temperature and volume. And we have the Gibbs free energy as a function of temperature and pressure. So to remember that, we draw this square here. We line up the natural variables in the corner. Entropy, pressure, volume, and temperature. And then we put the energy functions in the middle. Enthalpy, internal energy, Gibbs, and Helmholtz. So you can pronounce it ship, ug, vat to remember. Notice there's a pair of diagonal arrows pointing down. The arrow points towards the natural variable. Points towards the negative sign. So the differential of enthalpy is equal to temperature times the differential of entropy plus volume times the differential of pressure. Internal energy is going to be temperature times the differential of entropy minus pressure times the differential of volume. Gibbs free energy is going to be volume, you'll start with the opposite. So it's volume times the differential of pressure minus entropy times the differential of temperature. And then Helmholtz is going to be minus pressure times the differential of volume minus entropy times the differential of temperature. Now these 4 equations I just told you are for the closed system reversible process using pressure volume work only. Now, since internal energy is a function of entropy and volume, we can write out the equation like this. The differential of U is equal to the partial derivative of U with respect to S, holding V constant times the differential of S, plus the partial derivative of internal energy with respect to volume, holding entropy constant times the differential of volume. Now, another way we could say differential of internal energy is temperature times the differential of entropy minus pressure times the differential of volume. So, let's say we have constant entropy. Now let's do constant volume first. Then this term becomes 0. So then solving for t, we just get temperature is equal to the partial derivative of internal energy with respect to entropy, holding volume constant. Or likewise, if we hold the entropy constant somehow, then we just solve for p. So we get minus the pressure is equal to the partial derivative of internal energy with respect to volume, holding entropy constant. Now similarly, we have the differential of internal energy is equal to temperature times the differential of entropy minus pressure times the differential of volume. So let's say we have a constant volume process, so the differential of volume is equal to 0. Well, then the differential of U is going to be equal to just temperature times the differential of entropy. So we end up with, like I showed before, temperature is equal to the partial derivative of internal energy with respect to entropy holding volume constant. So remember, if we say that the differential of entropy is equal to 0, that means a constant entropy process. So then we could say, okay, the differential of internal energy is just equal to minus pressure times the differential of volume, which is how we found that minus the pressure is equal to the partial derivative of internal energy with respect to volume holding entropy constant. So doing the same for the other equations, we could say, okay, minus the entropy is equal to the partial derivative of Gibbs free energy with respect to temperature holding pressure constant. We could also say that volume is equal to the partial derivative of Gibbs free energy with respect to pressure holding temperature constant. We could say that temperature is equal to the partial derivative of enthalpy with respect to entropy holding pressure constant. We could say that volume is equal to the partial derivative of enthalpy with respect to pressure holding entropy constant. We could say that minus the pressure is equal to the partial derivative of Helmholtz free energy with respect to volume holding temperature constant. And we can also say that minus the entropy is equal to the partial derivative of Helmholtz free energy with respect to temperature if you hold volume constant, etc. So we have some of the most important measurable quantities, though, would be the heat capacity at constant pressure. The heat capacity at constant pressure we'll consider to be a function of temperature and pressure. Now remember, we said before, alpha is a function of temperature and pressure, and that was defined as 1 over volume times the partial derivative of volume with respect to temperature holding pressure constant, and that kappa is a function of temperature and pressure, and it's minus the 1 over volume times the partial derivative of volume with respect to pressure holding temperature constant. These two are important, because they can actually be measured experimentally. Now we can also say, okay, volume is a function of temperature and pressure, and PV is equal to nRT, assuming an ideal gas, obviously. So we showed before that for an ideal gas, alpha is just 1 over the temperature, and kappa is just 1 over the pressure. Now let's talk about the Euler reciprocity relation again. We already did this before, but it's important because we're going to use it again. So let's say that we have some variable z that's a function of x and y. Then we can write the exact differential. The differential of z is just the partial derivative of z with respect to x holding y constant times the differential of x, plus the partial derivative of z with respect to y holding x constant times the differential of y. We call this the exact differential of z. If you take differential equations, you'll learn about this. So we're going to call this side m. We're going to call this side n. Or no, we're just not the whole. Just this one term is m. Just this one term is n. So we're going to say the partial derivative of y times of the partial derivative of z with respect to x holding y constant is equal to the partial derivative of x, the partial derivative of z with respect to y holding x constant. We'll also say, okay, to simplify, we'll just say the differential of z is equal to m times the differential of x plus n times the differential of y. Now see handout 13. If the partial derivative of m with respect to y holding x constant is equal to the partial derivative of n with respect to x holding y constant, then we say the differential of z is an exact differential. If you took a differential equations, you already knew that. The partial derivative of m with respect to y holding x constant is equal to the partial derivative of n with respect to x holding y constant. That's the Euler reciprocity relation. Now that's important because the differential of any state function is exact. So the differential of u is exact, the differential of s is exact, the differential of g is exact, the differential of a is exact, and the differential of h is exact. Because internal energy is a state function, entropy is a state function, Gibbs free energy is a state function, Helmholtz free energy is a state function, and enthalpy is a state function. Now, if we have some variable that's not a state function, then the differential is not exact. For example, the differential of work or the differential of Q, heat, those are, they look similar, but they're not, those are not exact differentials. So given that what we just learned, remember we said the differential of internal energy is temperature times the differential of entropy minus pressure times the differential of volume. Therefore, by the Euler reciprocity relation, we can say that the partial derivative of temperature with respect to volume holding entropy constant is equal to minus the partial derivative of pressure with respect to entropy holding volume constant. And likewise, because the differential of enthalpy is equal to temperature times the differential of S plus volume times the differential of pressure, we can conclude that the partial derivative of temperature with respect to pressure holding entropy constant is equal to the partial derivative of volume with respect to entropy holding pressure constant. Likewise, because the differential of Helmholtz free energy is equal to minus pressure times the differential of volume minus entropy times the differential of temperature, we can conclude by the Euler reciprocity relation that the partial derivative of pressure with respect to temperature holding volume constant is equal to the partial derivative of entropy with respect to volume holding temperature constant. And likewise, because the differential of the Gibbs free energy is equal to volume times the differential of pressure minus entropy times the differential of temperature, by the Euler reciprocity relation, we conclude that the partial derivative of volume with respect to temperature holding pressure constant is equal to minus the partial derivative of entropy with respect to pressure holding temperature constant. See handout 14. Now, we talked about alpha already. Alpha will change with volume. So alpha is 1 over volume times the partial derivative of volume with respect to temperature holding pressure constant. Now remember, we said delta G is equal to 0 only when you're already at equilibrium. So let's talk about how these variables, internal energy, enthalpy, entropy, and Gibbs free energy, are dependent on temperature, volume, and pressure. Now technically we talk about the Helmholtz free energy because most of the time, real-world processes do not work at constant volume. So we're going to use the Euler reciprocity relations on the Gibbs equations to derive the Maxwell relations. So let's talk about application of the Gibbs equations and the Maxwell relations. So first, let's talk about the volume dependence of internal energy. What is the partial derivative of internal energy with respect to volume holding temperature constant? Now remember, temperature constant, that means isothermal. Well, we have the differential of internal energy is equal to temperature times the differential of entropy minus pressure times the differential of volume. We're going to hold temperature constant. So we're just going to put a subscript T here to show the temperature is constant. So we have the differential of internal energy at constant temperature is equal to temperature times the differential of entropy at constant temperature minus pressure times the differential of volume at constant temperature. Now we're going to divide by the differential of volume at constant temperature. So we have the differential of internal energy at constant temperature divided by the differential of volume at constant temperature, and that's equal to temperature times the differential of entropy at constant temperature divided by the differential of volume at constant temperature. We cancel like terms here, so we just subtract P. Notice how these are both at constant temperature. So we could just say, okay, the partial derivative of internal energy with respect to volume at constant temperature, and these two are the same, so it's equal to temperature times the partial derivative of entropy with respect to volume at constant temperature minus pressure. So now we're going to substitute using the Maxwell relation. Remember, the partial derivative of entropy with respect to volume holding temperature constant is going to be equal to the partial derivative of pressure with respect to temperature holding volume constant. So now, oh wait a minute, should there be a minus sign there? Wait, S and P. Nope, no minus sign, never mind. Okay, so we have the partial derivative of internal energy with respect to volume holding temperature constant is equal to temperature times the partial derivative of pressure with respect to temperature holding volume constant minus pressure. Now we're going to say, let's see, we're going to get, how does that happen? Okay, so we have the partial derivative of entropy with respect to volume holding temperature constant. That's equal to the partial derivative of pressure with respect to temperature. Uh-oh, I forgot something here. S over volume. PT, this should be constant volume. There we go. Okay, so we have the partial derivative of entropy with respect to volume holding temperature constant is equal to the partial derivative of pressure with respect to temperature holding volume constant. And that's actually equal to alpha over K. So now we have the partial derivative of internal energy with respect to volume holding temperature constant is equal to temperature times alpha over K minus pressure. This is true for any substance. Now it's interesting, all these quantities over here, temperature, alpha, kappa, and pressure, these are officially measurable quantities. The reason I say officially, there was a comment earlier how you can't directly measure temperature, but obviously in practice we do have a way of determining temperature. So for a perfect gas, remember we said that alpha is 1 over temperature and kappa is 1 over pressure. So the partial derivative of internal energy with respect to volume holding temperature constant is just going to be 1 over T times T over 1 over P minus P, simplifying, that equals 0 for a perfect gas. Now what about the temperature dependence of internal energy? So the partial derivative of internal energy with respect to temperature holding volume constant is equal to the heat capacity at constant volume. What about the temperature dependence of enthalpy? The partial derivative of enthalpy with respect to temperature holding pressure constant is just the heat capacity at constant pressure. What about the pressure dependence of enthalpy? Well, what is the partial derivative of enthalpy with respect to pressure holding temperature constant? We're going to use the Gibbs equation for the differential of enthalpy. So the differential of enthalpy is temperature times the differential of entropy plus volume times the differential of pressure. Now we're going to hold T constant. So we're going to put a subscript T here to show that it's constant. So we have the differential of enthalpy at constant temperature is equal to temperature times the differential of entropy at constant temperature plus volume times the differential of pressure at constant temperature. Now we're going to divide everything by the differential of P, pressure at constant temperature. So we have the derivative of enthalpy, we have the differential of enthalpy at constant temperature divided by the differential of pressure at constant temperature. That's equal to temperature times the differential of entropy at constant temperature divided by the differential of pressure at constant temperature plus volume. So now that these are both at constant temperature, so we can just say that's the partial derivative of enthalpy with respect to pressure at constant temperature times temperature. These are both with respect to temperature, so we can say that's the partial derivative of entropy with respect to pressure at constant temperature plus volume. Now we're going to substitute in using a Maxwell equation. So the partial derivative of volume with respect to temperature holding pressure constant is equal to minus the partial derivative of entropy with respect to pressure holding temperature constant. So now we have the partial derivative of enthalpy with respect to pressure holding temperature constant is equal to minus the temperature times the partial derivative of volume with respect to temperature holding pressure constant plus volume. Now remember we said alpha is 1 over volume times the partial derivative of volume with respect to temperature holding pressure constant. Therefore, alpha times volume is equal to the partial derivative of volume with respect to temperature holding pressure constant. So substituting that in, we get the partial derivative of enthalpy with respect to pressure holding temperature constant is equal to minus alpha volume temperature plus volume. And that should be true for any substance. What about the temperature dependence of entropy? Well, the heat capacity at constant pressure is temperature times the partial derivative of entropy with respect to temperature holding pressure constant. So we can say that the partial derivative of entropy with respect to temperature holding pressure constant is the heat capacity at constant pressure divided by temperature. Well, we know the heat capacity is greater than 0, and we know that the temperature is greater than 0. So we know that so if these are both positive, this has to be positive too. So we do know that the partial derivative of entropy with respect to temperature with holding pressure constant has to be greater than 0. Now what about the pressure dependence of entropy? Well, we know the the partial derivative of entropy with respect to pressure holding temperature constant is equal to minus the partial derivative of volume with respect to temperature holding pressure constant. That works out to just minus alpha times volume. What about the temperature and pressure dependence of the Gibbs free energy? Well, the differential of the Gibbs free energy is minus entropy times the differential of temperature plus volume times the differential of pressure. We're going to say we're constant pressure process. So we end up with just the partial derivative of Gibbs free energy, that's ugly, with respect to temperature. See if I can make that worse. But anyway, holding pressure constant is equal to minus entropy. So we could set the constant temperature, dt is equal to 0. So then we get partial derivative of Gibbs free energy with respect to pressure holding temperature constant is equal to volume. Now, let's talk about the Joule-Thomson coefficient. We did the Joule-Thomson experiment earlier, remember? So there's a partial derivative of enthalpy with respect to pressure holding temperature constant. That's equal to minus the heat capacity constant pressure times mu jt. Remember, mu jt, that's your Joule-Thomson coefficient. So mu jt is equal to the partial derivative of enthalpy with respect to pressure holding temperature constant divided by the heat capacity at constant pressure. So that works out to minus 1 over the heat capacity at constant pressure times, oops, I forgot a parenthesis, minus temperature times the partial derivative of volume with respect to temperature holding pressure constant plus volume. So we get mu jt is equal to 1 over the heat capacity constant pressure times temperature times volume times alpha minus volume. And that's going to just be equal to volume divided by heat capacity at constant pressure times the temperature times alpha minus 1. And this is true for any substance. Now remember we mentioned before that mu jt is equal to 0 for any perfect gas. Now what about take the heat capacity at constant pressure minus the heat capacity at constant volume? Well, we're going to end up with partial derivative of internal energy with respect to volume holding temperature constant plus pressure times the partial derivative of volume with respect to temperature holding pressure constant. Now remember, we said this term over here is called the internal pressure, and we're going to substitute for that. So we're going to get the heat capacity constant pressure minus the heat capacity constant volume is equal to alpha times the temperature divided by kappa, that's not kelvins, that's kappa, remember, minus the pressure plus the pressure times the partial derivative of volume with respect to temperature holding pressure constant. We're going to substitute for that. We'll get alpha times temperature over kappa, got the p's canceled out, times alpha times volume. Simplifying that, we get the heat capacity at constant pressure minus the heat capacity at constant volume is equal to alpha squared times temperature times volume divided by kappa. And this is true for any substance, and you'll notice all these quantities over here are observable. We can actually measure those in the lab. Now remember, for a perfect gas, we said heat capacity at constant pressure minus the heat capacity at constant volume is just the number of moles times the gas constant. As temperature approaches 0, heat capacity minus the heat capacity at constant pressure minus the heat capacity at constant volume approaches 0. So if the difference between them approaches 0, they must approach each other somehow, so the heat capacity at constant pressure approaches the heat capacity at constant volume. Now, if alpha is equal to 0, which is rare, but it is possible, then also in that case, the heat capacity at constant pressure will also be equal to the heat capacity at constant volume. Now, we mentioned before when I was talking about the British Petroleum oil rig incident that water, liquid water at least, has its highest density at about 3.98 degrees Celsius. So let's say we have pure water. We've got molar volume here as a function of temperature. So you notice higher than 3.98 degrees Celsius, the molar volume increases. And at lower temperature than 3.98 degrees Celsius, the molar volume increases. Now remember, rho, the mass density, is just mass divided by volume. That's lowercase m capital V. So that gives us the lowest molar volume is where it has the highest rho, the highest density. This is lowercase rho for density. So we have the partial derivative of molar volume with respect to temperature at constant pressure is equal to 0 down here. Remember, anytime you have a curve at the very top or the very bottom, the derivative will be equal to 0. Hopefully you learned that in differential calculus. So alpha is 1 over the molar volume times the partial derivative of molar volume with respect to temperature holding pressure constant. That's equal to 0. So what that tells us is that the heat capacity at constant pressure is equal to the heat capacity at constant volume for liquid water at 3.98 degrees Celsius. Now, usually the heat capacity at constant pressure is greater than the heat capacity at constant volume. We explained why for an ideal gas earlier on. It has to do with internal energy versus the PV energy. Heat capacity at constant pressure is always positive, and heat capacity at constant volume is always positive. Now, of course, because of this curve, because this density is lowest down here, that is why water, when it freezes, the solid is on top of the lake or the ocean or whatever, instead of the bottom. Now, most materials are the other way around, of course. Most materials, when they freeze, the solids will sink to the bottom instead of float to the top. Now, for a perfect gas, the partial derivative of internal energy with respect to volume holding temperature constant is equal to 0. And also, pressure times volume is equal to N times R times T. Now, for an ideal gas, PV is equal to nRT. Also, the partial derivative of pressure with respect to temperature holding volume constant is just N times R over V, because pressure is equal to nRT over V. Now, the partial derivative of internal energy with respect to volume holding temperature constant is going to be temperature times the partial derivative of pressure times the partial derivative of pressure with respect to temperature holding volume constant minus pressure. So substituting that in, we get temperature times nRP over V. This simplifies to P, so we just get P minus P is equal to 0. So I already mentioned this before. All ideal gases are actually perfect gases. That's why most books don't bother to explain any difference.